this is just a little bit of informal help on how to work on these type of practice questions. So in this particular practice, it's asking you to propose a synthesis scheme to make the acetals. Now, one thing about acetals is that whether you're breaking them apart or making them, it's going to give you the same reactants or the same compounds as your answer, because the molecules that we need to make an acetal are the same ones that will form when you break it back apart. Remember that breaking apart an acetal is hydrolysis because we use water to do it. So this particular practice exercise gave you 3 different structures and asked you to go ahead and figure out how to make them. So here's what I'm going to do. Let's start with this first one on the left. When I break this apart, the main thing to remember is that all acetals form initially from a structure that must have a carbonyl bond and must also have an OH bond, because that's where our initial reaction takes place. Those 2 oxygens are going to be found on this molecule. And in fact, you can see right away there's an oxygen here and an oxygen there. So when I go to do this reaction and break it apart, right away I can identify that where these 2 oxygens are connecting, which is always one individual carbon, must have been the carbon that was initially part of that carbonyl bond. Now let's use that information to figure this out. Let me clean this up a little bit. Because I have these 2 oxygens and the carbonyl carbon in between it, I'm going to start by essentially breaking apart the molecule at the 2 oxygens. That means, and I'll do a couple different colors to make this clear, I'm going to have one structure here, which was initially an alcohol. I'm going to have another structure over here that must have initially been an alcohol. And the remaining structure, which includes my carbonyl bond, must have initially been part of either an aldehyde or a ketone. So let's talk about that carbonyl molecule first. There's a carbon here, here, and here. So 3 carbons, and this carbon is connected to 2 oxygens in the acetal. But what that means is there's also an implied hydrogen. So right away I know that what I really have, and I'll just draw the carbons like this to make it clear, there's a hydrogen that was implied, and instead of 2 single bonds, which is what forms in the acetal, I know the reactant must have had a carbonyl. So again, that's this carbonyl structure that we need to make a hemiacetal and then an acetal. Now, it's not fully correct to write it this way, of course, because these carbons have to have hydrogens. So to make this correct, what I'm going to do is change this into a line structure because I just think it's easier to look at. So there's my line structure, and that is propanal. It's a 3-carbon aldehyde. All right, so let's now look at those other structures that we're dealing with. Let me go back and we'll deal with this one over here. This has 2 carbons on it. This must have initially been part of an alcohol. So again, there's my 2 carbons. There's the oxygen that we know is part of the reaction, but this must have initially been an alcohol, so that's ethanol. I'm going to do the same thing for my 3rd structure, which is here. This one's really short, it's just a carbon. So what that must have been is an oxygen, which was part of an alcohol. And to make it clear, I'll write a CH3 here. Okay, so that's methanol. So propose a synthesis scheme and show each step. You'll be able to see that in the answer, but what I should see in my answer, and I'll change my color here briefly, is here is an ethanol, here's a methanol, and here is a propanol. So let's go look at the answer for this. All right, so in this example, here's my propanol. I added methanol first, but you could just as easily use ethanol. And I drew my hemiacetal that forms before adding the second compound. Okay? So that structure or that reaction you should be familiar with from the lecture, but you can see it drawn out here. Let's go back and look at one more of these. On this second structure, I'm going to go ahead and erase what I have so far just to make it so this looks a little bit cleaner. Let's look at this second structure because it's a little bit unique, and I gave it to you purposely just to make you really kind of think a little bit hard. Okay, so I want to follow the same logic on this structure. I have 2 oxygens here and here, and that's where I'm going to have to break apart the bonds. when I break apart the bonds, I should be able to find two alcohols because that's what I need to make an acetal. One of them is here. We can see that's a 1 carbon alcohol. Now let's find the other one. All right, there's the carbon that was part of my carbonyl. So let me put this here. That's my carbonyl carbon. But when I go to break this apart, I see that this wraps around. Okay, I'm basically trying to break it apart and I'm getting this structure that just keeps going and going and going. What this means is this alcohol was actually part of the same molecule that had the carbonyl bond. So this is a carbon, a carbon, a carbon, and here's our carbonyl carbon. So imagine unraveling this, and what you actually have is there's the OH group, here's the first carbon, there's the second carbon, the third carbon, my fourth carbon is actually the carbonyl carbon. So that would be that structure there. And just like we saw in the previous example, there's an implied hydrogen here because right now there's 1, 2, 3 bonds, so there must be an implied hydrogen. So in this structure, the aldehyde is actually a much more complex molecule because it includes both the alcohol group and the aldehyde functional group. Now that may seem kind of unnecessarily difficult, but I did this for a reason. When we get to unit 7, we're going to see that monosaccharides, things like glucose and fructose, simple sugars, have this structure. And in fact, that's why we usually see our monosaccharides forming ring structures. That's going to become really important both in our unit 7 as well as in Chem 123. The other reason this matters is we learned that hemiacetals are most stable when they do make a ring structure. That's much more likely to exist than a hemiacetal that comes together from two different molecules. So this is actually a really relevant example. In this case, I would only need this orange and yellow structure to make the hemiacetal, and then the remaining structure will come from this other alcohol. Again, there's an OH, and it's just 1 carbon, which, because that looks weird, I'll write a CH3. As we scroll down to the answer, should be able to see that. So here it is, partly unraveled, making a hemiacetal. That doesn't require any catalyst or any special circumstances, but then I'll need an alcohol and an acid catalyst to complete the structure. So now you can try the third one on your own, but that's a little bit of help on how to think about breaking these apart.